Okay, we're going to go ahead and get started. So I guess many of you noticed there was, all the way on. There was no video for chapter 14. Not sure why, but so I will generate a video today as we go through class. So I have a little bit less time because I wanted to get some quicker questions in, talk about the next programming assignment, and get this lecture in. So I may be going a little faster, but it will be recorded and uploaded tonight, so you'll be able to watch it going forward. This material is important, but the algorithms that we're going to talk about, things like Gramschmidt Orthogonalization, whatever, you will not actually have to know how to implement them. You just have to know all of the properties of these things, not how to compute all of these things. So, am I recording? Yes, I'm recording. Okay, so yeah, this is covering material on general linear spaces. And if you didn't notice, we skipped 12 and 13. We will come back and get those. But those are also in the category of things that I want you to know some of the basics for, but I'm not going to have you implementing Gaussian elimination because the right solution is to use a library where it was professionally implemented and not actually go through all that detail. But linear spaces actually have an important understanding. The second part I'm going to cover today will be actually some things related to linear spaces as we use them in machine learning, which is actually an application of linear algebra, which is where your next assignment is going to be. So you might actually want to pay attention as we go through this part, because it is what's going to be part of related to homework program time. So the idea of general linear spaces is that when we're looking at things, until now we've done linear spaces as though they were just numbers in a vector space. So we've actually worked in a very particular space, Rn, where n was 2 and 3. R2, R3, 2 and 3 dimensions. But in general, linear spaces can be applied in any number of dimensions and in things that at first glance might not even seem to be linear. So in fact, this example drawing here is the linear space of all cubic polynomials over the interval between 0 and 1. Now these are all cubic polynomials, and that doesn't sound very linear, does it? But they are linear, as we'll go through. You'll see the properties that define a linear space doesn't mean that everything in them looks like lines and planes. It means that the way we operate on that space has the characteristics of a linear space. So they can live in higher dimensions, and in fact, at the very end of class today, we'll do one in infinite dimensions. Forget this finite stuff, why limit ourselves even to that? So, and using these higher dimensions can be very powerful. Almost all of the stuff that goes on in machine learning uses much higher dimensions than 2 or 3. We'll work in thousands, and as I said, sometimes infinite. So when we refer to dimensions, we're really going to think of them in a much more abstract sense. So 2 and 3, where I tried to give it, we started this class and I tried to give you some intuition about linear spaces because you can all think in 2 and 3D space. 4D is a little tougher. Maybe some of you can draw 4D. 5 is really hard to think about in terms of physical spaces. You know, 4D you can think of 3D plus time. You sort of get there pretty easy. 5 is tough. What's 1,000 dimensions mean? Well, dimensions simply are elements that we use to represent things. Every dimension. In X, Y, Z, that just happens to represent a physical point. But it could also represent RGB, so it's color, not physical space. I can represent any linear combination of bases. So the idea of a linear space in n dimensions And generally, we'll have boldface letters similarly, although I won't guarantee I'll remember to do that. And basically, operators on this space are defined by two very important operations. There's really a third, but we'll come back to that one, which is addition and multiplication by a scalar. And a linear space is something where linear combinations of things that started in this space are still in this space. So if I go back to that example with cubic polynomials, in the interval 0 to 1, if I add two cubic polynomials, I still get a cubic polynomial. If I multiply a cubic polynomial by a constant, I still get a cubic polynomial. And any linear combination, constant times one cubic polynomial plus constant times the next cubic polynomial, is still a cubic polynomial. And so that's why it's going to end up being a space. We'll go through a little bit more formally. So in a special case of this, why I said there's really a third property, which is the zero element. Every linear space has a zero element because this linearity property has to hold when S and T are both zero. So there has to be some special element in that space that is zero. So what do you think is the zero cubic polynomial? Zero. It's the polynomial that is zero, right? So that's it's a valid cubic polynomial. It doesn't have any coefficient for the cubic element, but it's still a valid cubic polynomial. So the properties of these linear spaces, in generalized linear spaces, we really think of things not as vectors in the simple sense, but vectors where the coefficients represent something. So if I think of this space defined by u equals the vector 1, 1, and v equals minus 2, 3, then the vector w equals 2 times this, whatever, right, is also an R2. So R2 is the vector space you've already all played with. But I can also think of another space, the space of 2 by 2 matrices. Now the rules of arithmetic operations on these also guarantee linearity. So all the vectors in W that satisfy R2 satisfy the property that they're greater than or equal to 0. And if I take any combination of matrices in 2 by 2 space, if I add 2 by 2 matrices, they're still 2 by 2. If I multiply them, they're still 2 by 2. If I multiply a constant and add them, they're still, right? So it has all the right properties. The same is true for all vectors in R2. Now, it's sort of interesting because I could also talk about all vectors, say, in R4. And in fact, there's a mapping between the linear space of all 2 by 2 matrices and the linear space of all elements of R4. Because, in fact, a 2 by 2 matrix is 4 elements. It's just a physical rearranging. But the rules for addition and multiplication aren't always the same. So when you talk about a vector space, you have to talk about what are the rules for adding elements and multiplying elements by a constant and doing all of the operations in that space. Oops. So if I let my space be defined by some set of vectors, in whatever vector space I'm in now, in n dimensions, I can talk about those vectors being linearly independent, by which we mean that if I compute some new vector as a linear combination, this combination will not have a solution set S1 through S0 for all possible things. So if they are linearly independent, then I can't write the first vector in this set as a linear combination of the rest of the set. So as soon as there's a vector in the set that I can't, now here I said the first, right? It's possible that I could write the first element of the set in terms of the second, but there exists some vector in the set which cannot be represented as a linear combination of the other ones. Then the set of vectors are linearly independent. So the zero vector can only be expressed in a trivial manner. So if I want the zero vector, then I have to write it when all of the coefficients are zero. That's the only way to get the zero vector. Okay, so those two things together give me my linearly independent set. And if the zero vector can be expressed in a non-trivial combination, then this set is called linearly dependent. And this is really just a generalization of what we call linearly independent in 2D and 3D. Right? If I had three vectors that I could write one as a combination of the other, then they were linearly dependent. Now there are some other things we noticed, like if one of the vectors was all zeros, one row or column was all zeros, then it's instantly linearly dependent. And that's true here as well, because if I had a column that was all zeros, or a vector that was all zeros, then I could put any multiple times that column and still get the zero vector, not only when they're all zero. So those same concepts still generalize to higher dimensions. So if we look at our subspace from this dimension, We call the subspace where we take any linear combination or all linear combinations of those vectors, we call that the space spanned by the vectors v1 through vr. So spanning, which again we saw in 2 and 3D, same idea here. If I have a bunch of 100-dimensional vectors and I consider this the possibility of all 100-dimensional vectors that I can get from those vectors, then that's the span of them. Now it doesn't mean that spanning all of them will give me the original n-dimensional space. If, for example, I have a bunch of vectors whose first 3 elements are non-zero and everything else is 0, then it doesn't matter how many of those vectors I put together, I can only span something that has the first 3 elements non-zero and everything else 0, which really is a subset of 3 dimensions, even though it has all these other fields in it. So span doesn't mean it fills the space, it just means it covers a particular subspace defined by these linearly independent vectors. If this subspace equals the whole space, then we call it a special term, which is it's a basis for that space. And if you haven't noticed in this chapter, I'm covering a lot of terminology. That is something you will be responsible for. There will be lots of terms, and you should know what all of them mean, even if you can't compute them all. Right? I will not ask you to compute. I might ask a simple basis question, but I'm not asking a very complicated basis question. I might ask something simple about what's spanned by. That's really just to understand, if you understand what the ideas are. If our Ln is a linear space of dimension n, then because it's only of dimension n, any set of n plus 1 vectors must be linearly independent. In 3D, I can only have 3 linearly independent vectors. I can't have 4 or 5. In 100D, I can only have up to 100 independent vectors, not 101, not 102, because after that, there's no dimensions left for them to fill up. Some of them are redundant. Okay. That doesn't mean if I have 101 vectors that they automatically are a basis for the space, because they still might not cover it all. They might not even span the space, even though there's more of them than you need. So I can be linearly dependent and still rank deficient, which we'll come back to. So as an example, if I think about this vector here, v equals 3, 4, 7, I can write that as a linear combination of E1, E2, and E3 in R3, right? So we can write any vector as a linear combination of those 3 vectors. These 4 vectors, including v, would then be linearly dependent, because I can write one as a combination of the others. Okay. That kind of question you should be able to do. If I give you a set of vectors and I ask you if they're linearly dependent or independent, you should be able to compute that, because it's really just figuring out, is there a linear combination of these that allow you to solve that. So any one of these 4 vectors form a subspace of R3, any 2 of them form a 2-dimensional subspace of R3, any 3 of these 4 vectors form a 3-dimensional subspace of R3, all of R3. Okay, again, one more example here. We have an R4. There are now 4 vectors. These vectors, even though there's only 3 of them in R4, they're still linearly dependent, because V2, this middle one, can be written as the first one plus 2 times the second one. Or maybe it's the other way around. That's what it says, but I think it's 2 times the first one plus the second one. I just got to type over. Or minus 2 times this one. So there's combinations of them that put them together. Just apologize if those numbers are wrong. No, as I said, I think this. I don't know why that's written down there. It should be something like V3 minus 2V1, right? Because that would give me 3 minus 2 would give me 5. The zeros would Okay, yeah, if I do minus 2, you're right, I'll get minus 2 on the bottom. So these vectors are not linearly independent. This is an example straight out of the book. Whoops. I should have checked them. Let's hope this one's right. So we have R3. Let's see if this one's right. V3 is minus V1 plus V2, 2V2 plus V4. That's true. 2 times this one gives me, no. How about minus V1 plus V2 plus V4? I don't know what they did. So Yeah, so obviously I'm going to have to fix this in the video. Okay, so correcting the book is left as an exercise to the reader. It's a classic math problem. So yes, those don't quite work out. I will fix them. It's also possible it's not right out of the book. I am dyslexic, so it's possible. It is right out of the book? Okay. I was trying to give them a credit because maybe I typed something wrong, right? I can do that. I do it a lot. Yep. Great. So I should check. The book actually has an errata page on the publisher's website. I should check that and see if it's there. Okay. Oh, what fun. So where were we? So basically, despite the fact that the book doesn't do it correctly, you should be able to figure out if a linear combination of them works. Now, in this case, because there are 4 vectors, they must be linearly dependent. So there must be a combination of 3 of these 3 that give me this one. It's just not the one that was written here. Right, so that one works. So there's nothing on the bottom. So there's one V4. So V4 plus V2 gives me V3. I don't have to do anything else, right? So great. Even though I'm recording, I will have to re-record stuff. Okay. So from the linear map point of view, so now we've talked about the linear spaces. Linear maps, it's just too hot. If I put it there, I'll forget it. Linear maps, as we had for R2 and R3, are like matrices, except now we're just going to view them as transformation, because they may not be implemented as a transformation matrix. Okay, because we actually talked about other things like affine maps, right? Affine maps added a constant, so it's not just matrix. Oops. So affine maps are still linear. They're just not matrix multiplication anymore. So we're going to have this general idea of a linear map that transforms one space to another. So here we have an n-dimensional space being transformed to an m-dimensional space. And the important thing about linear maps is they preserve the linear relationship. If I have 3 points, or 3 vectors, v1, v2, v3, in the linear space Ln, and I map it to Lm, where I get images A, I'm going to get images A times V1, A times 2, right? Then they have to satisfy the linearity property. If I take any linear combination of those 3 vectors in Ln, I get the same linear combination of the mapped vectors in Lm. That's the linearity property. Okay? Maps without this property that don't satisfy this for all values of alpha and beta, including 0, are nonlinear maps. So I can still have a map between anything. I can always have a map. It just may not be a linear map. So if the linear map is a matrix, M by N matrix A, right, then we can represent our mapping given the vectors into 2 spaces by applying the matrix A to the vector. Right? Not all linear maps are vector or matrices, but all matrices are linear maps. Right? So we can always go that direction. We can have functions that are more complicated than just a matrix computation to get there, but they'll have this equivalence. Okay? When we do that, we can talk about the output vector v prime in terms of a new coordinate system, which is a constant from the constants from each of the subdimensions times the new basis vector in the n-dimensional space. And we call that the column space of A. So if I have a matrix in 3D, right, when I have my matrix, I can look at columns or rows. If I look at each of the columns of my matrices, we call that the column space. Right? So now I have 3 vectors, they represent the column space. And if my matrix is M by N, then it has M rows and N columns. So it'll have n-dimensional, N vectors in its column space, each of which are m-dimensional vectors. Right? So what would I get for the row space? Right, I'll get m rows each of which are of dimension n, right? So I can talk about the row space and the column space. They don't represent the same things because they actually have different dimensions if the matrix is in general m by n. And so when I talk about doing operations, I can relate either row space or column space depending on what it is I want to do. So going back to our maps, if I have the vector, the map A from R2 to R3, I represent that as a column, as two column vectors, right? Each of which is three-dimensional, so I have 3 rows, and I have 2 of them, and that gives me my mapping from R2 to R3. So if I multiply a 2-dimensional vector by this matrix, I'm going to get a 3-dimensional vector. Hey. So given these vectors, when you multiply by this matrix, you get these vectors. And they're right. Good. That's good. So the VI are linearly independent. And in fact, you know they have to be linearly independent when I have these vectors in R3. Why do they have to be linearly dependent? Despite the fact that it actually works out that way, but anytime I have a mapping from R2 to R3, if I take 3 vectors in R3, it has to be linearly dependent because I only had 2 dimensions to begin with. Right? So there's only spans 2-dimensional space in R3. Right? It's a 2-dimensional subspace because it has rank 2, because rank is determined by the minimum of the number of the column or row rank. So you can just tell by looking at it, it'll be a deficient space even though it's in R3. And you can see that this map still satisfies the linearity relationships. So when we talk about rank, which is what I was just talking about, we're talking about matrix rank. We're going to generalize the concept a little bit. Until now, we worked mostly with square matrices, although we talked a little bit about other ones. So if I have an m by n matrix, it can be at most rank k, which is the minimum of m and n. In fact, it's the minimum of the row rank or the column rank. Either of those is at most m or n independently. Okay, and the rank equals the number of linearly independent columns, which is also equal to the number of linearly independent rows. Doesn't really matter which one I look at. If the rank is equal to the minimum of m and n, then we call this matrix full rank, even though it's not square. Right? And if it's less than the minimum of m and n, then we call it rank deficient. So we had a 3 by 3 matrix. If it had rank 2, it was rank deficient. If I have a 3 by 2 matrix and it has rank 2, then it's still full rank. Even though it has 3 rows, it's still full rank because it only has 2 columns, and so we still consider it full rank. So slightly changing the definition of full rank from what you might have thought it was, because for square matrices, we didn't have to worry about the difference. Okay. A linear map can never increase the dimension, and it can't increase the rank. So I can map something to a higher dimensional space, but it can't actually increase the dimensionality of the subspace it works in. The last example we looked at, right? I said it's always going to be, if I have 2 column vectors, so I'm mapping 2D to 3D, I can have at most a 2-dimensional subspace. Will I always have a 2-dimensional subspace? Yes? No? No? Tobias, why not? Right, so if I have two vectors that are actually the same, then when I map it, I'll have a 1-dimensional subspace. If I have 2 zero vectors, I have a no-dimensional subspace. It's 0. So, but it can never increase it, which was actually, we already talked about before the midterm. You can't increase ranks by multiplying by other matrices. You can decrease it, but you can't increase it. So if I actually have a matrix and I want to figure out what is the rank, one way of doing it is to basically use Gauss elimination, or the forward elimination part of Gauss elimination, until the matrix is in upper triangular form, and then the number of non-zero ranks is the rank of what you get. So if I were to take a bunch of matrices and convert them, I can have something that is deficient. When I get done with it, it'll have some rows that are 0. Right? So the top ones are things that are full rank, and the bottom examples are rank deficient matrices. So when I do Gauss elimination, I eventually get some zeros on the diagonal and then all to the right of it, and I will have a rank deficient matrix. I get a full row of zeros. So just as numeric examples, if I want to determine the rank of a matrix, and I'm going to go through the forward elimination, now I'm not going to make you, we're not going to do any of these examples today because we haven't done the higher dimensional Gaussian elimination. Although you actually know all the steps, it's the same as we did for 3D. You just keep doing it for every element of the matrix. It just gets real annoying by hand, so we're not going to bother with it. So if I did forward elimination, right, so in this case I'd get rid of the 0, I'd get rid of this 1 by subtracting the first row, and then I'd get rid of this one by adding the first row, and then I get all zeros here. Then I do some more work on the next column, and then the last column. You'll see in this case you get a row of zeros. In practice, you really won't have to worry too much about this, because in practice, if you want to ask the rank of a matrix, you will be calling a library that will answer rank, right? Because you'll call a library that did the Gaussian elimination stuff for you. But it's important that you know the properties, because the rank deficient property means that my map doesn't actually do the dimension I want. So again, in the 2D or 3D analogy, if I have a map that's mapping stuff to 3D, but it's rank deficient, what does that mean about where I can go in 3D? So I know I have a map that's taking 3D, but the map is itself, I have a 3D space, I multiply by a map that is rank deficient, so it has rank 2. What does it mean about where my points go in 3 space? Really? Right, so in fact, it's always a planar subset of 3D at most. It could be a line, but no, it's a rank 2. I said it's rank 2, then it's a plane, right? So it doesn't matter that I multiplied by this matrix, and now everything lives on a plane. And if I work in 100 dimensions, and I multiply by something that has rank 10, then even though I'm in a 100-dimensional space, I will now only have a rank 10 subspace, and everything else. Now, it doesn't mean that they will all be zeros, right? For homework assignment program 4, I so oversimplified it. I didn't realize this, right? Some of you came from office hours. You can actually solve most of it without doing much linear algebra, because you could just do trig and whatever, because all the planes were parallel and you knew what's going on, right? The real problem, they would be skewed planes, and you have to figure out like dot products and the real linear algebra stuff. So then you have to work in these higher dimensions, but they were still planes, right? They were still 2-dimensional subspaces in 3 space. You just have to do the representation and treat them that way. So these linear maps have this property that they're doing this. Now, just like we talked about matrices and the idea of inverting a matrix, which we haven't spent a lot of time on, but if I want to solve AX equals B, we could talk about the inverse, right? We did that in 2D and 3D. So an n by n matrix that has rank n is always invertible. So if the matrix has full rank, it means it maps the whole space to the whole space, which means there's a way to map backwards, right? So any linear map that is full rank is invertible, and vice versa. Any square matrix that is full rank is invertible, and it also goes the other way around. If it's invertible, it must have full rank, because it means it's preserving the mapping's dimensionalities. Okay. If it's invertible, it does not reduce the dimension. So that tells you a couple things. The determinant must not be 0. So whatever that matrix is, you know it doesn't have 0 determinant, because there is volume before you started, and volume is not 0. It's not preserved. The matrix might have a very small determinant or a very large determinant. So area and volume is mapped, but it's not 0. Okay. It measures the determinant of that matrix, measures the volume of the n-dimensional parallel pipette defined by the column vectors. So if I look at my matrix as a bunch of column vectors, then that forms some parallel pipette in space, and that 0, right? So again, in 3D, right, we can draw these, right? They form some vector, right? And those vectors, here's my coordinate space, right? Those vectors then form a parallel pipette, right? In 3 space. And the volume of that is what the determinant is. In 3D, the volume makes a lot of sense to you. In 100 dimensions, volume is a little bit more complicated, but it's really just the same thing. It's the volume of treating all of these things as though they were things and multiplying them together. Right? You get volume by taking length times width times height. With this parallel pipette, you have to do a little bit more work to deal with the angles. Same thing happens in higher dimensions. So That now covers the basics of linear spaces and linear maps. We'll do a quick clicker question. Engagement so far. I don't know. Oh, it's waiting. There we go. Okay, last call on that. Okay, so now we're going to get to what actually is a very important part of linear spaces, and one of the reasons they're so useful is this idea of inner products, which is really just a generalization of the idea of dot products. So the inner product is a mapping from this n-dimensional linear subspace to the real numbers. And so just like in a dot product, I went from two vectors to a scalar, right? That's two n-dimensional objects into one dimension. That's what we're looking at. The inner product has some important properties. The first is symmetry. The inner product of V and W is the same as the inner product of W and V. So order doesn't matter. Homogeneity. If I multiply one of the elements by alpha, that's the same as multiplying the inner product of the two original vectors by alpha. Right? And notice that this holds even when alpha is 0. The additivity property says that if I take an element and I add u and v and do the inner product with w, that's the same as doing the inner product of u and w added to the inner product of v and w. And you can sort of see that this gives it some very linear-like properties because I can multiply them by scalars, I can add them, and the inner product behaves properly as a linear operator across those. And the final one is positivity, which is an added constraint that says that the inner product of a vector with itself is 0 if and only if the vector is 0. So if I go to do the dot product, right, and I get a value of 0, is that always 0? Only if the vector is 0? So if I do a dot product of a vector times itself, think about what that is, right? That's the square root of v1 squared plus v2 squared plus whatever, right? So if all the numbers are real numbers, squares can only be greater than 0, right? If any of them is greater than 0, then the sum will be greater than 0. So that actually does hold. It's not a property we talked a lot about, but it's a property that did hold for our dot product. And a dot product is a proper inner product. Okay. Now, this positivity property is not between two other vectors. V and W can be 0 frequently when neither one of them is 0, right? We call those orthogonal. But if I go back to these and I look at the homogeneity and additive properties together, we get that any linear combination, alpha u plus beta v w, is equal to alpha times the inner product of u and w plus beta times the inner product of v and w. So this satisfies the linearity property and hence is a linear map. Okay? It's a linear map from n-dimensional vector space, wherever these v and w live, into the real space. Okay, and as we said, the inner product, the dot product is an example of one of these. But as we will see, it's not the only one. It's by far the most common, but it's not the only one. So if we define this sort of test idea of an inner product in R2, so here's an inner product. Given v and w, we're going to define the inner product as 4 times the first element v1 times w1 plus 2 times the vector v2 times w2. Okay, so does that actually satisfy the properties of being an inner product? If I told you that was my inner product, we have to check. So the first is, well, does it, when we go to compare it, does it do the right kinds of things? So first, if I were to take this product and I take 2 special vectors, and this is a nice, useful thing, right? Let's look at the special vectors 0, 1, 1, 0. If I take the inner product of E1 and E2, I get 0, right? So that inner product, when I fill them in, is 0, consistent with what we expected from those. How about the linearity, homogeneity property? Is this homogeneous? Homogeneity. Multiply one of them by alpha, right? So if I multiply either v or w by a constant, this gets multiplied by a constant. So yes, because they work through. Right? If they're additive, does this work through? I'm not going to go through all the math, but yes, this has the additive property. So the last question is positivity. Is it 0 if and only if v and w is 0? So if I put in the same vector, like E1 and E1, right, then I'm going to get 4 times this, and whatever value is in the first item will still be there. So this ends up satisfying all of those items. If I now start using it with other things that take some other unit vector, so I want to go back and check, right, so now I put in E1 times R2, right, I multiply all this out, I get that this unit vector doesn't have the same length when it gets done. Yes.
Where does the 4 and 2 come from?
Oh, they're just made up numbers. They're just randomly chosen.
Are they necessary for this? Or do you just do
No. So are they necessary? We're trying to show you how do you test that something is or is not an inner product. So it's just an example. Now, why you would want to use this test inner product, that's a different question. I'll actually show you one later on where we actually do use an inner product that looks very weird. You won't see where it comes from, but it's very important in various places in machine learning where we want to invent new inner products to allow us to do things in inner product spaces instead of doing more complicated math. But right now it's just getting through what is the properties. Does that answer you? Okay. So as I said, we've already gone through the symmetry property is easy, right? Because it doesn't matter which one's called U, which one's called V, right? Homogeneity, we talked through that one. Additivity, again, it sort of goes through. And then positivity, right? We just start squaring each of the individual elements, and that's 0 if and only if. So this does satisfy it. Coming back to Nathan's question, I'm not sure how useful this one is. This is not one I have seen used in any useful way, but it's not that far from some of the other ones we will use that have this weird interactions that you'll get to see. So, I can't think of one place where you might end up with inner products that look like this. A classic place where you end up with this kind of what we would call rescaling inner product is if I'm combining things where my units, for other reasons, are not always consistent. So if somehow somebody measured the first element of a vector in, say, quarts, and the second in pints, and the second in quarts or whatever, right? Then this multiplying by 2 and 4 might be so that when I go to actually do the inner products, I get things that are actually meaningful in some final set of units. Because when I do the inner product, I'm taking this element times this element plus that element times an element and combining it back to a scalar. So I can actually be doing some scaling as part of that process. So I can leave my database or whatever in whatever units they want and still get the right products out. So there are some reasons to come up with one. Whether or not this one's meaningful, I don't know. So some terms that get redefined now that we have inner products. So we will talk about the length or the distance between two vectors, but we can do that now entirely in terms of inner products. So the Euclidean norm is the square root of the inner product of two elements. And if you think about what we did, right, that's still true for your dot product. You took the dot product of V times V, you got the sum of the squares of each of the individual elements. Well, once I start working with less obvious things, then the Euclidean norm might be weird. So if I go back to that space I talked about in the beginning of cubic polynomials, you can actually define an inner product over that space, and then you can talk about the norm of a cubic polynomial, because it makes sense in that space. You have to be a little careful. The norm is now a function of the space in which it's defined. So I could actually have the same, in fact, the same matrix with different norms depending on how I interpret the space that matrix represents. Because the inner product, I can have the same dimensional space and have multiple inner products on it. As we just saw here, this is an inner product in R2. If I use this inner product and ask what's the norm of a matrix, I will get a very different answer. Right? It's not it's just a different norm because I used a different inner product. And when it's the usual norm, we often ignore the subscript just as a, right? Then the distance between two vectors, because these are vector spaces, subtracting two vectors is always a vector in the space. So when I do u minus v, right, which I can do because it's a vector space, then I can do its inner product with itself, and I get that the distance from u to v is the inner product of u minus v with itself, take the square root. So it's like the Euclidean, right? And all these are just generalizations of that concept we saw for dot products. So if we go back to that test inner product, we can sort of define what its norm means. So the norm of the E1 vector in the normal dot product sense is 1, but the norm of the E1 vector in this new inner product space, even though it's in the same dimensional space, is 4. It's a rescaling inner product, and so this space just changed units to be 4. The distance between E1 and E2, which in the normal space is the square root of 2, right? It's the hypotenuse of that triangle. Now it's this weirdly scaled hypotenuse of a triangle, and so it's 4 times the distance, the difference squared, plus 2 times the distance squared, which gives me the square root of 6. So again, you might be saying, why would I ever do that? Well, when we get to these high-dimensional machine learning things, a lot of what we'll end up doing is we will use these properties and know they exist, and then we'll be working in a space where we don't even know exactly what those spaces mean, right? So again, the idea of scaling between pints, quarts, and cups is a very non-intuitive thing, but if that's what somebody gave me data in, I might want to work in that space so I could work in it. If I work in these more complicated spaces, they make sense. But coming back to inner products, we can actually talk about inner products going back to those like polynomials, right? I can actually talk about the product between two different functions in this space. So here I'm going to do the inner product for each point in a curve, and if I do, the black line here is showing you what is the dot product, and the gray line is showing you this test inner product. So it's doing some rescaling. And some of those things are not so obvious, because for some functions, it's going to, you know, might make what looks like an almost straight line look like a wavy line, right? But sometimes that's useful, as we'll see when we start doing separators when we get to machine learning. Sometimes I want to separate things that have a non-linear boundary between them. And by using these weird inner products, I can make a linear operator that has boundaries that seem nonlinear. They're still linear, they're just linear in a different space. With our concept of inner products, we can now define orthogonality. When we define orthogonality between U and V is when their inner product is 0. Just like we said two vectors in Rn were, when their dot product was 0, they were orthogonal. This is true in n dimensions, except now we don't say just the dot product, which is a special case, it's the general inner product. And we can define an orthogonal basis for that space. And in an orthogonal basis, each of the vectors in our basis are mutually orthogonal, which means if I have two vectors in my basis, I and j, their inner product is 0. And the inner product of I times I is 1, then we call this thing an orthonormal basis. They can be orthogonal but not have unit length, and then it's just an orthogonal basis. An orthonormal basis has each of these having a length 1. To get there, there's a method called Gramschmidt. And Gramschmidt will produce a linear take any linear space and produce an orthonormal basis. We're actually not going to cover too much about how to do that. I'll briefly show you 1 or 2 slides on it. But you do need to know that that is the purpose of Gramschmidt. Because if you want to call a library because you want orthonormal basis, an orthonormal basis, you'd want to know, oh, I got to call the Gramschmidt method in this library to do that. So pragmatically, why might I care about having orthonormal bases? Can you think of any reason why you might want to have things that were orthonormal? So if they're orthogonal, it means as soon as they're orthogonal, I know that I can represent any final answer as a linear combination of those pieces. And I don't have to worry about the pieces interacting. Each column, if you think of the original orthonormal basis, E1, 0, 0, right, all of those are orthonormal bases. This is a generalization of that concept, to higher dimensional spaces, but also the things that might be rotated. But an orthonormal basis gives me the equivalent of a frame that is I could rotate back to the normal space. The other is, once they're orthonormal, we've talked before about implicit representations and how in an implicit representation I can measure distance by just plugging into the formula. If I build that representation using orthonormal basis, they're already normalized, so I can just plug in the right representation and measure distances by plugging to those bases by plugging stuff in. Two more properties we want to get through for inner products. So in the concept of linear spaces, we can now talk what are called inner product spaces. And in an inner product space, there's an added constraint called the Cauchy-Schwarz inequality, which says that the inner product of V and W squared is less than the inner product of V times the inner product of W. Now that might seem really weird. Why would you ever care about that? But this is simply, in the inner product space, a generalization of something you've already seen before in high school, which was the triangle inequality, right? Where if I have a triangle, right, I have A, B, and C, I know that C has got to be less than or equal to, C squared has got to be less than or equal to A squared plus B squared, right? This is called the triangle inequality, the lengths relating two sides of a triangle to the other. The Schwarz inequality is really almost the same thing, because if I think about this now, this is the inner product from V and W. This is the inner product of W with itself. This is the inner product of V with itself. And this is the generalization of that triangle to much higher dimensions to get the same kinds of things. The equality in this holds if and only if V and W are linearly dependent vectors, right? Which is then your triangle collapsed to a line. Because if V and W are linearly dependent, then they have the same direction. And then the hypotenuse is equal to the sum of those two pieces, instead of less than. So from that, with a little bit of effort, the same way we derive the relationship between a dot product cosines and angles, you get that the angle cosine theta is given by the inner product of V and W divided by the norms of V and the norms of W. So the same thing we saw for a dot product, except now this is true in these more general concept of inner product spaces. But it's the same thing you saw for dot product. You just replace almost every property you knew for the dot product. You can replace the word dot product with inner product, and they still hold. But there's these other things that have inner products that are not dot products. Okay, so since we know these properties from the dot product, right, we know that the norm is greater than 0, the norm is 0 if and only if the vector is 0, alpha, so it's linearly scalable, and the fourth, the triangle inequality, which is derived from the Cauchy-Schwarz inequality. So all of these are true of our inner product spaces. So if I have a space in which I have an inner product on top of it, now I can do a whole bunch of operations in that space as though it was almost the same as working in Rn. So I can compute distances, I can do a bunch of other operations, rotations, transformations of the space. So the projection, which is one of the operators we talked about before, also makes sense now in these inner product spaces. So if I have a span U1 through UK, that are a subspace of my overall linear space, then if U is a vector not in that subspace, then I can do an orthonormal or orthogonal projection by doing the inner product of some vector V with each of the basis vectors, and that will give me a projection into the final space. Right. So all of the operations we were working on before, all of those still apply. So this is one, how to do a projection in higher dimensional space. You should be able to do that one because it's really just a generalization of stuff we saw before. You don't have to dig deep to find those. Okay, one more engagement question. Last call on that? Okay, so I'm going to go through this next section on Gramschmidt Orthogonalization very quickly. I want you to understand some very high-level generalities of it. I will not ask you to actually do it, but you should know sort of the high ideas of why we're doing it and what we can do with it. So since every inner product space has this idea of an inner product, we're going to use those inner products to define this idea of an orthonormal basis. Given the basis, there's a number of operations that I can do because now I can choose to work only over the basis instead of over all possible elements of the space. So given some set of vectors B1 through BR, we want to find the subspace of that where n is greater than or equal to r. We want to find the item that is orthogonal to the given basis. Okay, so this is actually a little bit more general than just find a set of orthogonal bases. This is given r things that are orthogonal, find a new thing that is orthogonal to it, to that subspace. And the nice thing about that property is you can use it for other things. So when we were, for example, trying to find the reflection of a point about a plane or a line, we did that by actually projecting orthogonal to that plane, finding the distance, finding the foot, and going the other way that same distance. So if I wanted to reflect a point around some arbitrary subspace, I can use Gramschmidt to allow me to do that because I can find the basis for that subspace, project orthogonal to it, double the distance, and I get the same construct that allowed you to work in 2 and 3 dimensions, but now I'm doing it in 1,000 dimensions where I don't even know what they mean, and I don't even necessarily know when I start what does orthogonal mean in a general sense, because I don't know which of the 1,000 dimensions are actually meaningful. There might only be 50, or there might be 999. So when I'm trying to find orthogonal, I have to work through that process in a computational or pragmatic way. So the basic idea of Gramschmidt then is to find the orthogonal projection, and we already briefly mentioned that from the linearity property, we get that this projection is, if I want to find the projection some new vector u, I can take u dotted with my current bases vectors, or inner product. So u inner product b times b1 plus u inner product b2 times b2 dot 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 up to u inner product br times br. And that gives me a projection that's into the orthogonal subspace. Okay, now how we prove that all of that happens, I'll go through a very brief geometry explanation on the next slide, but you don't have to know how it's true. You just recognize that I can use Gramschmidt to take a bunch of vectors, and it's pretty simple. I just take a bunch of inner product with my current set of vectors, and I get one that's orthogonal to it. That's only true if the vectors are already an orthogonal basis. So I can add one more, I get a new orthogonal basis, then I can add one more, and I can keep doing this process. And that's how I build an overall basis. To check the orthogonality, you just sort of put it back in and do the dot product, or the inner product, and you find everything sort of goes away. So if we think of this geometrically, to build the basis, I start with one vector. With one vector, it's a basis of one-dimensional subspace, and I don't really have to worry about it. If I want to make it orthonormal, I simply have to divide by its norm, and I get my orthonormal first element. To get my second element, I'm going to take a second vector, and it doesn't really matter what vector I take as long as it's not parallel to the original one. So I'm trying to give this second vector. I project it, I subtract v2 minus that projection, and I divide by its norm, and that gives me my next orthonormal basis, and so on. So you sort of walk this up, adding one vector to another and another. So if I have my first vector, here's just 4 vectors. My first orthonormal vector is just the first one. The second one, which we're not going to run through all of the math, is I take this vector dotted with that vector. Right, go back to what I did here. Oops. Right, I take the projection. So in this case, the projection is just the inner product is a dot product. So I take this one dotted with that one, subtract it from the first one, and then divide by the norm. And that's where the square root of 3's come from, because by now with all these ones here, I get the square root of 3 in my norm. For the next one, I take this next vector, and I continue the process. I project it onto this, I project it onto that, subtract them, and go through that. So, and I build up my vectors that way. Again, I'm not going to actually ask you to do it. I just want you to have a general idea what are the steps in the process, even though you won't have to implement it. Okay, so we're going to go through a gallery of spaces. We're going to look at some specialized linear spaces that get used. Is that a question, Ryan?
No.
Oh, scratch. Okay, I understand that. We're going to go through some examples of some specialized linear spaces that get used a bit, and then I'm actually going to take it into machine learning, where I will talk even more about how it gets used in machine learning. Although we'll do the machine learning part after break. So linear spaces whose elements are all polynomials of a fixed degree n, where n is any degree you want. So all linear polynomials are a linear space, but so are all quadratic polynomials, so are all cubic polynomials. Anytime I say the space of all polynomials of a degree, they all have the right properties. Addition in the space by a coefficient, I just multiply the coefficients and leave everything else the same. But notice that multiplying them by a constant doesn't actually make the final computational result of that polynomial, right, is multiplied by a constant, because the coefficients just get multiplied. But if I multiply x, or t in this case, by a constant, that's not linear, right? It's linear in the space of its coefficients, not in the space of the parameter t. T is nonlinear, the coefficients are linear. So to just sort of see that that's a linear, right, we can check its properties. So if I take two of them and I multiply them by a constant, add them together, I get yet another polynomial of the same degree. If I go to test the zero property, all of those will work out. So that polynomials now are a space in which we can apply linear algebra, because we have all this linear algebra stuff we've been talking about. We can measure the distance between two polynomials by measuring the distance between their coefficients and knowing their degree. That lets us know what's the norm, or the distance, right? When we talk about the distance between P and Q, right? Well, P and Q can now be polynomials, and you can still measure their distance. Okay, so that's the kind of thing where we get some very powerful things when we start moving up. For those of you, by now you've probably all taken calculus, you should have, right? The derivative operator, which you met in calculus, it turns out the derivative operator is also a linear map. Right? You looked at it in lots of ways, but in any space in which I can compute the derivative, it is a linear operator. It is a linear map. So if I take the derivative of a polynomial of degree n, I get a polynomial of degree n minus 1, right? Which is still formally a polynomial of degree n, because it just has one coefficient that's always 0, but it still lives in the same space. Right? It's a subspace of the space, but a subspace of the space is still allowed for our definitions of a linear map. So the rank of this map, the derivative operator, is n minus 1. Now, we actually did this here for the space of polynomials, but that's true in general. The derivative operator is always a linear operator, and it's a rank reduction operator. It reduces, it's always a linear operator. It's not always a rank reduction operator. Because when I take the derivative of a cosine, I get a sine. Right? It keeps all of its ranks and stuff the same. It does in simple spaces, but I don't think, I think the answer is no. It doesn't always maintain independence. Well, in fact, it can't when it's a reduction operator, right? Because I can take two things that were not the same, but after the derivatives, they are the same, right? And so I violate the rules of independence that way. So two cubic polynomials in the space of linearity, you should be able to put them together, show all of the elements are true, and then you can apply the derivative operator, because you should all be able to, I'm not going to actually make you do derivatives, so you don't have to worry too much if you're very rusty in that, but you should know that they were there. You should, however, if I give you any space, be able to answer, does it satisfy linearity, because it's just applying those four properties. A linear space is given by the set of all really valued functions over the interval 0 to 1. So this is now a space whose dimensionality isn't finite. The space of all continuous functions. There are uncountably many of those. And there's no great way to represent them all, but the space still has the properties that if I take a linear combination of continuous functions over the interval 0, 1, it's still a continuous function over 0, 1. And it satisfies the zero property, it satisfies homogeneity, it satisfies symmetry in terms of the operations. Okay? It just doesn't have a finite representation. So until all the other ones before this, everything sort of looked like I had a bunch of coefficients. I could treat them as a matrix. This is an example of a linear space where there is no matrix representation. Because it's infinite dimensional, the matrix just doesn't happen. But I can still do lots of operations on it.
And for this space, there is no finite basis vector. There's a way of getting generator functions which provide some kind of basis, but not the same. As we already mentioned, any set of matrices of all the things in that matrices, or a 3 by 3 matrix, is a linear space. So the space of all n by n, the space of all n by m matrices are going to be linear things as well. Some more abstract examples, although the space of continuous functions is pretty abstract. The set of all linear maps from linear space n dimensions, there's a space associated with that which we call the dual space. Its dimension is the same as that of the original space, but it's defined by the set of all linear maps from that space onto itself. So, and if you recognize this, you're now going to see there's this progression of issues, right? I have some linear space. Now I define the set of all linear spaces, or the set of all linear maps from this space into the reals. That is also a linear space, which means that the set of all linear maps from that space into the reals is a linear space, which means the set of all maps from that space, right? So you can just chain these guys up and make all kinds of linear spaces. So this type of linear map that goes from a linear space to the reals is called a linear functional, a term I will not actually make you remember because we won't use it very much, but in case you see the word, a functional is a mapping from from a linear space of n dimensions into the real numbers. And it's like a functional because a function maps a bunch of stuff to one number. This is a functional that maps a linear space into a space of one numbers. So it has a bunch of the same kinds of properties. So considering the fixed vector, the inner product of this space, right, we can define an inner product which is u1 minus u2, where this is based on terms of the dot product, right? So any dot product with this gives us a space. If I take any two vectors e1 and e2, I can associate with them, and this linear map then satisfies all the right properties of being itself linear, and I can apply all of the other properties to it. So it has an inner product space where its inner product, which is now the inner product in the space where v is our fixed vector, is just induced from the other properties. So that last section I realized was a little bit abstract. We'll do for a quick engagement on this, and then we will take a break, be back by 5 of. Don't know, send me mail. So I have 2 meetings I'm trying to schedule, which might put me up in Denver, might not, so don't know yet. So.
Yeah, I'll just send you an email with available times because I need to talk to you for, I think, a senior audit.
Okay, well, senior audit you do with your main hall advisor, but we can still go over everything. That's fine.
Yeah, that's fine. Because you're the head of the.
Yeah, so I'm your faculty advisor. You have 2 kinds, right? So,
I still have to talk to you for
advising.
So.
Yeah.
Cool.
Okay.